Deep in the endless cosmic ocean, invisible to human eyes for billions of years, tiny crimson specks have been waiting. They existed when the universe was young, when galaxies were still learning how to form, when the first light was just beginning to pierce the primordial darkness. For most of cosmic history, these mysterious objects remained hidden, their secrets locked away by the tyranny of distance and the limitations of our telescopes. But in the summer of 2022, less than 6 months after the James Webb Space Telescope opened its golden eyes to the cosmos, astronomers noticed something profoundly strange. They appeared as little red dots scattered across the deepest images ever captured of the infant universe. Compact, bright, impossibly red. At first glance they seemed almost insignificant, mere pinpricks of light among countless galaxies. But as astronomers began to study these crimson curiosities more carefully, a sense of unease crept through the astronomical community. These objects shouldn't exist. Or rather, they shouldn't be able to exist in the way they appeared to exist. They were too massive, too bright, too early in cosmic history to make sense according to our well-tested theories of how the universe evolved. Some astronomers began calling them universe breakers, a dramatic term that captured the tension these discoveries created. Were our fundamental models of cosmology wrong? Had we missed something essential about how galaxies and black holes form? Or were these tiny red dots revealing something even more extraordinary? Something that had been theorized for decades but never observed? Black holes born not from dying stars but from the Big Bang itself? To understand the significance of these mysterious objects, we need to travel back to Christmas Day 2021. On that morning, from a launch pad in French Guiana, an Ariane 5 rocket lifted off carrying the most sophisticated observatory ever constructed. The James Webb Space Telescope, a collaboration involving NASA, the European Space Agency and the Canadian Space Agency, represented decades of engineering ambition. Its primary mirror, composed of 18 hexagonal segments, coated in a microscopically thin layer of gold, spans more than 6 meters across, making it the largest mirror ever sent into space. But size alone doesn't capture what makes the James Webb Space Telescope revolutionary. Unlike the Hubble Space Telescope, which primarily observes visible and ultraviolet light, JWST specializes in infrared wavelengths. This might seem like a technical detail, but it fundamentally transforms what the telescope can see. Infrared light has a longer wavelength than visible light, which means it can penetrate dust clouds that would completely obscure optical observations. More importantly for our story, infrared light is precisely what we need to observe the most distant, and therefore oldest, objects in the universe. This is because of a phenomenon called redshift. As light travels through the expanding universe, its wavelength gets stretched, shifting toward the red end of the electromagnetic spectrum. The farther light travels, the more extreme this stretching becomes. Objects from the very early universe, whose light has been travelling toward us for more than 13 billion years, have had their original ultraviolet and visible light stretched all the way into the infrared. Before JWST, these ancient objects were essentially invisible to us. The Hubble Space Telescope could glimpse some of them, but only the brightest examples. JWST, with its enormous mirror and exquisite infrared sensitivity, was specifically designed to peer into this previously hidden realm. After its launch, JWST embarked on a month-long journey to its final destination, a gravitationally stable point in space called Lagrange Point 2, about 1.5 million kilometers from Earth. There, it deployed its enormous sun shield, a 5-layer structure the size of a tennis court that keeps the telescope's instruments cooled to temperatures just above absolute zero. In the months that followed, engineers meticulously aligned each of the 18 mirror segments, a process so precise that the entire mirror had to be smoothed to within a fraction of the wavelength of light. Finally, in July 2022, the first science images were released to the public. the astronomical community held its collective breath. What would this incredible machine reveal about the early universe? The answer came quickly, and it was more puzzling than anyone anticipated. Among the galaxies captured in those first deep field images, astronomers noticed a peculiar population of objects. They were small, appearing as tiny dots even in JWST's extraordinarily detailed images. They were faint, requiring hours of exposure time to detect. But most distinctively, they were profoundly red, standing out like ruby droplets against the cosmic tapestry. These weren't the familiar spiral or elliptical galaxies that populate the nearby universe. They were something different, something astronomers had never seen before. Within weeks, research teams around the world began studying these objects in detail. The initial observations came from several large survey programs, including the Cosmic Evolution Early Release Science Survey, known by its acronym SEERS, which was one of the first major observing programs to use JWST. As astronomers sifted through the data, they found these little red dots again and again. They weren't rare flukes, they were numerous, scattered throughout the deep images of the early universe. The first detailed analysis came from a team led by Ivo Labbe, then at the Swinburne University of Technology in Australia. Labbe and his colleagues identified 6 of these objects and attempted to determine their nature through photometric analysis, essentially studying how bright they appeared in different infrared filters. What they found was deeply troubling. Based on their brightness and colour, these objects appeared to be galaxies from approximately 500 to 700 million years after the Big Bang, placing them in an epoch when the universe was less than 5% of its current age. That timing alone would have been remarkable, but it was what the analysis suggested about their masses that caused alarm. If these were indeed galaxies, they appeared to contain stellar masses rivaling that of the Milky Way, our own galaxy, which has had more than 13 billion years to accumulate its 100 billion stars. These objects, however, would have assembled all that mass in just a few 100 million years. According to our best models of galaxy formation, this should have been impossible. Stars take time to form. Small galaxies need time to merge into larger ones. The universe at that early epoch simply shouldn't have had enough time for such massive structures to assemble. This was the origin of the universe breakers moniker. If these observations were correct, they threatened to break our standard model of cosmology, known as lambda CDM, which had successfully explained countless other observations of cosmic structure formation. The tension was immediate and intense. Some astronomers suggested that perhaps our understanding of the universe's age was wrong, that maybe the cosmos was older than we thought, giving these massive galaxies more time to form. Others proposed more exotic solutions, including modifications to the fundamental physics of gravity or dark matter. But not everyone was convinced that these objects were what they initially appeared to be. As more data accumulated and more sophisticated analysis techniques were applied, a different picture began to emerge. The little red dots might not be massive galaxies at all. They might be something even stranger. The key insight came from spectroscopy, the technique of splitting light into its component wavelengths to reveal detailed information about an object's composition, temperature, and motion. Unlike photometry, which gives us a rough sketch of an object's properties, spectroscopy provides a high-resolution fingerprint. As various research teams obtained spectroscopic observations of little red dots, they discovered something unexpected. Many of these objects showed spectroscopic features characteristic of black holes actively consuming matter, a phenomenon astronomers call an active galactic nucleus, or AGN. When matter falls toward a black hole, it forms a swirling disk that heats to millions of degrees, emitting tremendous amounts of light across the electromagnetic spectrum. This light has distinctive spectral signatures, including broad emission lines from gas moving at thousands of kilometers per second in the black hole's gravitational grip. Dale Kuchevsky, an astronomer at Colby College in Maine, led a major effort to compile and analyze spectroscopic data from little red dots. his team eventually gathered observations of 340 objects, making it the largest sample of these enigmatic entities studied to date. What they found was striking. Between 70 and 80% of the little red dots showed clear evidence of containing actively accreting supermassive black holes. The light wasn't coming primarily from stars at all, it was coming from black holes feeding on surrounding gas. This revelation solved one problem, but created several new ones. If the light was coming from black holes rather than stars, then these objects weren't as massive as initially feared. The universe-breaking aspect seemed to fade, but the discovery of black holes introduced its own set of profound mysteries. These black holes appeared to be supermassive, containing millions of solar masses, and they existed when the universe was less than 1 billion years old. The question of how such enormous black holes could form so quickly remained deeply puzzling. Moreover, these weren't ordinary supermassive black holes like the relatively sedate one at the centre of our Milky Way. These black holes appeared to be growing rapidly, consuming matter at prodigious rates. The galaxies hosting them were tiny, much smaller than typical galaxies in the modern universe. In some cases, the black hole's mass approached or even exceeded that of all the stars in its host galaxy combined, a situation essentially never seen in the present-day cosmos, where supermassive black holes typically represent only about 0.1% of their galaxy's stellar mass. The distribution of little red dots across cosmic time added another layer to the mystery. They weren't evenly distributed throughout the history of the universe. Instead, they appeared in large numbers starting around 600 million years after the Big Bang, reached a peak abundance and then underwent a rapid decline, becoming much rarer by about 1.5 billion years after the Big Bang. Whatever these objects were, they represented a specific phase in cosmic evolution, a brief but important chapter in the story of how galaxies and black holes came to be. As observational data accumulated throughout 2023 and 2024, the little red dots revealed themselves to be even more peculiar than first impression suggested. Every new piece of information seemed to deepen rather than resolve the mystery. The objects defied easy categorization, sitting uncomfortably between the types of cosmic structures astronomers were familiar with. One of the most perplexing aspects was their extreme compactness. When astronomers measured the physical sizes of these objects, they found them to be extraordinarily small compared to typical galaxies, often just 2% the diameter of the Milky Way. Yet they glowed with luminosities that suggested enormous amounts of energy generation happening in that minuscule volume. This presented an immediate problem. If the light came from stars, as one early theory proposed, then the stellar density in these objects would have to be staggeringly high, reaching levels that seemed physically implausible. Imagine a region of space smaller than the distance from the Sun to its nearest stellar neighbour, Proxima Centauri. Now imagine packing not just a few stars into that volume, but hundreds of billions of them, creating stellar densities thousands or even millions of times higher than anything we observe in nearby galaxies. The night sky on a hypothetical planet in such a galaxy would be dazzlingly bright, illuminated by countless suns packed so closely together that individual stars would barely be distinguishable from one another. The gravitational interactions in such an environment would be chaotic, with stars constantly experiencing close encounters that would fling them out of the galaxy or send them plunging toward the centre. But the star formation interpretation faced another, even more fundamental problem. To create such enormous stellar populations so quickly after the Big Bang would require star formation rates far exceeding anything observed anywhere in the universe, past or present. Stars don't form instantaneously. They require clouds of gas to collapse under gravity, a process that takes millions of years for individual stars and potentially much longer for entire stellar populations. The little red dots, if they were star-forming galaxies, would need to have been churning out new stars at rates that challenged our understanding of the physical limits on star formation. The alternative interpretation that these objects were powered primarily by accreting supermassive black holes seemed more promising in some ways, but introduced its own set of problems. The spectroscopic signatures supported this view. Many little red dots showed broad emission lines in their spectra, particularly in hydrogen's Balmer series, indicating gas moving at velocities of hundreds or thousands of kilometers per second. Such extreme velocities are characteristic of material swirling around black holes in the intense gravitational fields near the event horizon. Additionally, some objects showed emission from highly ionized elements, another telltale sign of the extreme energetic environment around an active black hole. When a black hole accretes matter, it doesn't do so quietly. The infalling material forms an accretion disk that reaches temperatures high enough to emit X-rays and ultraviolet light capable of stripping electrons from atoms, creating a zone of highly ionized gas around the black hole. Yet even this interpretation had problems. One of the most puzzling features of little red dots was what they didn't show. Supermassive black holes in the nearby universe, when actively accreting, are prolific X-ray sources. The hot inner regions of their accretion disks shine brilliantly in X-rays, making them some of the brightest X-ray sources in the cosmos. Astronomers expected little red dots, if they contained actively feeding black holes, to be easily detectable in X-ray observations. But when astronomers pointed the Chandra X-ray Observatory, our most sensitive X-ray telescope, at fields containing little red dots, most of them remained stubbornly invisible in X-rays. A few showed X-ray emission, confirming they did contain accreting black holes, but the vast majority were X-ray silent. This was completely unexpected, and contradicted the standard picture of how accreting black holes behave. Several explanations were proposed for this X-ray mystery. Perhaps the black holes were surrounded by thick clouds of gas and dust that absorbed the X-rays before they could escape, making the sources appear X-ray weak or invisible. Computer models were constructed to test whether such obscuration could account for the observations. The results were mixed. While heavy obscuration could reduce X-ray emission, the extreme levels needed to completely suppress X-rays in so many objects seemed physically questionable. Another possibility was that the black holes themselves were accreting in an unusual manner, different from the standard model of thin accretion disks. If the black holes were consuming matter at rates exceeding what's known as the Eddington limit, the maximum rate at which a black hole can accrete matter before radiation pressure pushes the infalling material away, then the accretion disk structure might be fundamentally different. Super Eddington accretion can create thick, puffy disks where radiation becomes trapped, potentially altering the X-ray emission properties in ways that current models don't fully predict. The spectroscopic analysis revealed yet another oddity. When astronomers examined the detailed emission line spectra of little red dots, they found that these objects lacked many of the high ionization emission lines typically seen in active galactic nuclei. Lines from ions like carbon-4 and helium-2, which require extremely energetic photons to produce, were often weak or absent. This suggested that either the radiation field around these black holes was softer, containing fewer high-energy photons than expected, or that the gas structure was arranged in a way that prevented the high ionization lines from forming. The mass ratios presented perhaps the most profound challenge. In the local universe, there's a well-established relationship between the mass of a supermassive black hole and the mass of stars in its host galaxy. Typically, the black hole represents about 0.1% of the galaxy's stellar mass. This scaling relation suggests that black holes and their host galaxies co-evolve, growing together over cosmic time in a delicate balance. But little red dots violated this relationship dramatically. In many cases, the black hole's mass appeared to be 10%, 20%, or even 40% of the total stellar mass. Some astronomers went further, suggesting that in the most extreme cases the observed light could be explained entirely by the black hole with essentially no galaxy visible at all. When Dale Krzyzewski's team used models to subtract the black hole's contribution to the light, some little red dots effectively disappeared, implying the galaxy component was either extremely faint or perhaps not present in any substantial form. This observation pointed toward a radical possibility. What if, in the early universe, black holes didn't form after galaxies, growing gradually over time as the standard picture suggested? What if black holes formed first, and galaxies assembled around them later? This would flip our understanding of cosmic structure formation on its head, suggesting that black holes played a more fundamental role in shaping the early universe than previously imagined. In late 2024, a team led by Benjamin Leyer at Penn State University and Steen Voits at the University of Bath proposed a bold new interpretation of the little red dots. They suggested these objects might represent an entirely new class of cosmic entity they called black hole stars. In this model, a supermassive black hole sits at the centre of a massive dense cocoon of gas. The gas is cold compared to typical accretion disk material, perhaps only a few thousand degrees rather than millions. The black hole feeds on this gas at an extraordinary rate, releasing tremendous amounts of energy, but the dense cocoon absorbs and re-radiates that energy at much cooler temperatures. The result would be an object that looks like a star on the surface, glowing with relatively cool red light while containing a voraciously accreting black hole at its core. The team analysed an extreme example of a little red dot they dubbed the cliff, discovered during the Rubies survey, which obtained spectra of 4,500 distant galaxies. The cliff showed precisely the spectroscopic signatures the black hole star model predicted. Emission from cold gas mixed with evidence of an actively accreting black hole. If this interpretation is correct, it has profound implications. Black hole stars might represent a phase of extraordinarily rapid black hole growth, a period when supermassive black holes can accumulate mass at rates far exceeding what standard accretion theory allows. This could help explain one of the biggest mysteries in modern astrophysics: how supermassive black holes containing billions of solar masses could exist less than 1 billion years after the Big Bang, when starting from stellar mass black hole seeds and growing at reasonable rates should have taken far longer. But perhaps the most intriguing possibility raised by the little red dots is that they might not be products of stellar evolution at all. Perhaps these objects are our first glimpse of something theorized for more than 50 years, but never definitively observed: primordial black holes, created not by the death of stars but by the Big Bang itself. In 1971, a young British theoretical physicist named Stephen Hawking published a paper that would haunt and fascinate cosmologists for decades. The paper proposed a radical idea: black holes might not only form from the collapse of massive stars. In the extreme conditions of the very early universe, immediately following the Big Bang, black holes could have formed directly from the primordial soup of matter and energy that filled all of space. The idea emerged from contemplating the nature of the infant universe. In the first moments after the Big Bang, the universe was incredibly hot and dense, far beyond anything we can recreate in particle accelerators today. The entire observable universe was compressed into a volume smaller than an atom, with densities and energies that stretched our understanding of physics to its breaking point. As space rapidly expanded in the first fractions of a second, this primordial material began to cool and dilute, but the process wasn't perfectly smooth. Quantum fluctuations, the inherent uncertainty built into the fabric of space-time itself at the smallest scales, created tiny variations in density throughout the early universe. Most of these fluctuations were inconsequential, evening out as the universe expanded. But Hawking realized that in some rare locations, these density variations might have been extreme enough that gravity immediately took hold, causing a region to collapse inward before expansion could smooth it out. If the density in such a region exceeded a critical threshold, if it collapsed to a size smaller than what's called the Schwarzschild radius for that mass, a black hole would form. These primordial black holes would be fundamentally different from the black holes we see forming in the modern universe. Stellar black holes, created when massive stars exhaust their nuclear fuel and collapse, are limited to a relatively narrow mass range, typically between a few solar masses and perhaps a few tens of solar masses. Supermassive black holes at galaxy centres contain millions to billions of solar masses, but we believe they grew to those sizes gradually over cosmic time, starting from smaller seeds and accumulating matter over billions of years. Primordial black holes, however, would be constrained only by the conditions in the early universe when they formed. In principle, they could have any mass. Small primordial black holes, with masses comparable to asteroids or even smaller, could have formed in the very first instant after the Big Bang. Larger ones, perhaps forming slightly later when the universe had expanded and cooled somewhat, might have masses ranging from a few solar masses up to hundreds of thousands or even millions of solar masses. The timing of formation matters enormously. Hawking's calculations showed that the universe's conditions were right for primordial black hole formation during specific windows of cosmic history. The earliest would have formed in the Planck era, less than 1/trillionth of a trillionth of a trillionth of a second after the Big Bang, when quantum effects of gravity were dominant. Later generations could have formed during the quark-gluon plasma phase, when the universe was filled with a hot soup of fundamental particles, or during the quantum chromodynamics transition, when quarks bound together to form protons and neutrons. A 2024 review by Bernard Carr and colleagues concluded that the most likely period for substantial primordial black hole formation was during the quantum chromodynamics epoch, occurring less than 100,000th of a second after the Big Bang. This would have resulted in a mass distribution with several distinct peaks, the most prominent one around the mass of our Sun. The concept of primordial black holes remained largely theoretical for decades after Hawking's original paper. There was no observational evidence for their existence, and many physicists questioned whether the conditions needed for their formation would actually occur in realistic models of the early universe. But the idea never completely disappeared, kept alive by its potential to explain several cosmic mysteries. One of those mysteries is dark matter. The universe contains roughly 6 times more mass in the form of dark matter, which we can detect through its gravitational effects, but which doesn't emit or absorb light, than in the ordinary matter that makes up stars, planets, and everything we can directly observe. The nature of dark matter remains one of physics' greatest unsolved problems. Could some or all of dark matter be composed of primordial black holes? If so, they would be nearly impossible to detect directly, as small black holes don't emit light, and would be incredibly difficult to observe through their gravitational effects alone. Numerous searches have been conducted to constrain the possible contribution of primordial black holes to dark matter. Gravitational microlensing surveys, which look for brief brightening of distant stars when a massive object passes in front of them, have ruled out primordial black holes in certain mass ranges as the dominant form of dark matter. Observations of the cosmic microwave background radiation, which would be affected by the presence of primordial black holes during the universe's first few 100,000 years, have provided additional constraints. However, these observations haven't completely ruled out primordial black holes. Depending on their mass distribution and formation history, they could still make up a significant fraction of dark matter, particularly in mass ranges that are difficult to constrain observationally. And there's another possibility, one directly relevant to our story of the little red dots. Even if primordial black holes don't constitute most of dark matter, they might still exist in numbers sufficient to play a crucial role in the formation of cosmic structures. This brings us back to the supermassive black hole problem. JWST's observations have revealed that supermassive black holes containing millions or even hundreds of millions of solar masses existed less than 1 billion years after the Big Bang. According to the standard formation scenario, supermassive black holes begin as stellar mass black holes, perhaps 50 to 100 times the Sun's mass, created when the first massive stars explode as supernovae. These seed black holes then grow over time by accreting gas from their surroundings and by merging with other black holes when galaxies collide. The problem is one of timing. black holes can't grow arbitrarily fast. There's a physical limit called the Eddington limit, set by the balance between gravity pulling matter inward and radiation pressure from the hot accretion disk pushing matter outward. A black hole accreting at the Eddington limit can roughly double its mass every 50 million years. Starting from a stellar mass seed of 50 solar masses, even continuous Eddington-limited accretion over 800 million years could only grow the black hole to about 800,000 solar masses, far short of the millions of solar masses observed in early supermassive black holes. Astronomers have proposed several solutions to this problem. Perhaps the early black holes accreted at super-Eddington rates, exceeding the theoretical limit through mechanisms we don't fully understand. Perhaps they had particularly dense environments that allowed rapid growth through frequent mergers. Or perhaps the seeds weren't stellar mass black holes at all, but heavier seeds formed through different mechanisms. This is where primordial black holes enter the picture. If black holes with masses of thousands or even hundreds of thousands of solar masses formed directly from density fluctuations in the first second after the Big Bang, they would have a massive head start. They wouldn't need to grow as much to reach supermassive sizes, and they would have been present in the universe before the first stars even formed. In this scenario, the first stars and galaxies might have assembled around these primordial black holes, with the black holes serving as gravitational anchors that accelerated the formation of cosmic structures. Andrea Ferrara, an astrophysicist at the Superior Normal School in Pisa, Italy, has been investigating this possibility. In research published in 2025, Ferrara and his colleagues analysed some of JWST's deepest observations, looking at light sources at redshifts beyond what had been confirmed before. They found 9 objects at extraordinarily high redshifts, 6 at redshift 17 and 3 at redshift 25. These correspond to times when the universe was only 200 million to 100 million years old. The remarkable thing about these objects is that they appear to emit ultraviolet light during an epoch when stars shouldn't yet have formed. According to our best models of structure formation, based on how dark matter clumps under gravity and how ordinary, matter cools and condenses, the first stars probably didn't ignite until the universe was at least 150 million years old. But JWST was detecting bright ultraviolet sources at earlier times. Ferrara and his team proposed that these early light sources weren't stars at all. They were primordial black holes, already massive, already in place, beginning to consume gas from their surroundings. As matter fell toward these black holes, it heated up and emitted light, potentially making primordial black holes, rather than stars, the first significant sources of illumination in the cosmic darkness. The hypothesis remains controversial and is not yet widely accepted. The observations are at the very edge of JWST's capabilities, and there's considerable uncertainty in determining the exact redshifts of these objects without detailed spectroscopy. Some astronomers caution that the objects might be lower redshift contaminants, or that they might be unusual but still star-forming galaxies whose properties we don't fully understand. But there's another observation that has lent weight to the primordial black hole hypothesis. In September 2025, a team led by Ignace George Barlis at the University of Cambridge reported detailed observations of an object called QS01, one of the little red dots, discovered behind the massive galaxy cluster Abell 2744, also known as Pandora's cluster. The cluster's gravity acts as a natural lens, magnifying the light from more distant objects behind it, allowing astronomers to study objects that would otherwise be too faint to observe in detail. QS01 exists at a redshift of about 10, meaning we're seeing it as it appeared roughly 600 million years after the Big Bang. The team used JWST's spectroscopic capabilities to measure the velocity of gas swirling around the central object, a technique that allowed them to determine the black hole's mass. What they found was astonishing. A black hole containing approximately 50 million solar masses. That mass alone makes QS01 remarkable. But what makes it potentially revolutionary is the nature of its environment. When George Barlis and his colleagues looked for evidence of the galaxy hosting this black hole, they found almost nothing. The gas surrounding the black hole appeared to be pristine, composed only of hydrogen and helium, the primordial elements that emerged from the Big Bang. There was no evidence of heavier elements like carbon, oxygen or iron, which are created inside stars and dispersed when stars die. This observation is crucial because it suggests the black hole formed before any significant star formation occurred in that region of space. In the standard scenario, stars form first, enrich their environment with heavy elements, and then some of those stars die to create stellar mass black holes. But QS01 appears to have reversed this sequence. A massive black hole exists in a nearly starless environment, suggesting it might have formed directly, without a stellar progenitor. Roberto Maiolino, a professor at the University of Cambridge and Cavendish Laboratory who collaborated on the QS01 study, called it a paradigm shift. The observation suggests that at least some supermassive black holes in the early universe didn't grow from stellar seeds, but instead formed through a more direct route. Primordial black holes represent one such route, though not the only possibility. The mass of QS01's black hole, 50 million solar masses, is considerably larger than most theoretical models predict for individual primordial black holes, which typically range up to about 1 million solar masses. But this doesn't necessarily rule out a primordial origin. If multiple primordial black holes formed in the same region, they could have merged quickly in the dense early universe, or the initial primordial black hole could have grown rapidly through aggressive accretion in its pristine environment. Distinguishing between these scenarios observationally is challenging. We need more objects like QS01, more detailed observations that can constrain the environments and formation histories of early black holes. We also need to better understand the range of masses and formation mechanisms that primordial black holes could have. Theoretical work continues to refine our predictions, exploring different inflationary models and conditions in the early universe that might give rise to primordial black holes with various properties. What makes the primordial black hole hypothesis particularly compelling is not just that it could explain individual objects like QS01, but that it offers a unified explanation for several puzzles simultaneously. It could account for the early appearance of supermassive black holes. It might explain why little red dots show such unusual mass ratios between black holes and their host galaxies, if the black holes formed first and galaxies assembled around them later. It could even potentially contribute to dark matter, though this remains more speculative. The hypothesis also has the virtue of being testable. Primordial black holes would have left specific imprints on the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. As our observations of the microwave background become more precise, we should be able to detect or rule out these imprints. Future gravitational wave detectors might detect mergers of primordial black holes, which would have distinctive properties compared to mergers of stellar mass black holes. Stephen Hawking himself noted one particularly interesting prediction about primordial black holes. According to quantum mechanics, black holes aren't completely black. They emit a faint radiation, now known as Hawking radiation, through quantum effects near their event horizons. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass and supermassive black holes, the Hawking radiation is far too cold and faint to detect. But for small primordial black holes, with masses comparable to large asteroids or small moons, the Hawking radiation could be much warmer and potentially detectable. Intriguingly, very small primordial black holes, those with masses around 100 billion kilograms, would be completing their evaporation through Hawking radiation right now, approximately 13.8 billion years after the Big Bang. Their final moments would produce a burst of gamma rays. NASA's Fermi Gamma Ray Space Telescope has searched for such bursts and hasn't found clear evidence of them, which places constraints on how many small primordial black holes could exist. But these observations don't rule out larger primordial black holes, including those in the mass range relevant to little red dots and early supermassive black holes. While primordial black holes offer an elegant solution to the mystery of early supermassive black holes, they're not the only possibility. The scientific process requires us to consider multiple hypotheses and test them against observations. Several alternative formation pathways have been proposed, each with its own strengths and challenges. The most thoroughly developed alternative is called direct collapse black holes. This scenario, which has been extensively studied through computer simulations and theoretical calculations, proposes that under specific conditions in the early universe, massive clouds of primordial gas could collapse directly into black holes without first forming stars. The direct collapse scenario begins with large clouds of hydrogen and helium gas, perhaps 100,000 times the mass of the Sun, sitting in gravitational wells created by dark matter concentrations. Normally, such a gas cloud would fragment as it cooled, breaking into smaller clumps that would eventually form individual stars. The key to preventing fragmentation is keeping the gas hot enough that it can't efficiently radiate away its energy and condense into smaller structures. In the modern universe, or even in the universe a few billion years after the Big Bang, this would be impossible. Gas clouds naturally cool through several mechanisms, particularly through the emission of infrared radiation by molecules like molecular hydrogen. But in the very early universe, conditions might have been different. If a cloud of primordial gas was bathed in intense ultraviolet radiation from nearby star-forming regions, this radiation could dissociate molecular hydrogen, breaking the molecules apart into individual atoms. Without molecular hydrogen, the gas would lose its main cooling mechanism, staying hot and flowing smoothly toward the center of the cloud without fragmenting. As the gas accumulated at the cloud's center, it would become denser and hotter. Eventually, the temperature would reach millions of degrees, and the gas pressure would temporarily halt the collapse. At this point, the central region would contain what theorists call a quasi-star or supermassive star, an exotic object never seen in the modern universe, with a mass perhaps tens of thousands of times that of the Sun. But this object wouldn't be stable. As more matter piled onto it from the surrounding cloud, the core would be compressed to ever higher densities and temperatures. When the temperature reached about 1 billion degrees, a new cooling mechanism would kick in: neutrino emission. At these extreme temperatures, particle collisions can create neutrinos, ghostly particles that interact so weakly with matter that they stream freely out of the star, carrying away energy. This neutrino cooling would cause the core to collapse rapidly, forming a black hole with a mass of perhaps 10 to 20 solar masses. However, this wouldn't be the end of the story. The collapse of the core would happen while vast amounts of matter were still falling inward from the outer parts of the cloud. This matter would continue to fall onto the newly formed black hole at an enormous rate, potentially orders of magnitude higher than the Eddington limit. Under these conditions, the black hole could grow explosively, reaching masses of 100,000 to 1 million solar masses in less than 1 million years. This scenario has been developed in detail through sophisticated computer simulations by researchers including Priyamvada Natarajan at Yale University, Marta Volonteri at the Institut d'Astrophysique de Paris, and many others. The simulations show that direct collapse black holes are indeed possible in principle, but they require very specific environmental conditions. First, the gas must be metal-free, containing essentially no elements heavier than helium. Even tiny amounts of heavier elements would allow dust grains to form, and dust is an extremely efficient coolant, preventing the gas from staying hot enough to avoid fragmentation. This requirement means direct collapse black holes could only form from pristine primordial gas that had never been enriched by star formation. Second, there must be a source of strong ultraviolet radiation to dissociate molecular hydrogen. This radiation, in a specific wavelength range called the Lyman-Werner band, must be intense enough to keep the gas hot, but not so intense that it ionizes and disperses the gas. The required conditions are fairly narrow, suggesting direct collapse black holes would be relatively rare. Third, the gas cloud must be massive and the gravitational well must be deep. This typically requires dark matter halos with masses above a certain threshold, roughly 100 million solar masses. Such halos were rare in the very early universe, but became more common as cosmic structures grew. Given these stringent requirements, theoretical predictions suggest direct collapse black holes would have been uncommon, perhaps with only a few forming per cubic megaparsec by the time the universe was 1 billion years old. But uncommon doesn't mean unimportant. Even a small population of massive seed black holes could have had a disproportionate impact on cosmic structure formation, serving as the nuclei around which the first massive galaxies assembled. Observationally testing the direct collapse scenario has proven challenging, but JWST is beginning to provide crucial evidence. One of the key predictions is that direct collapse black holes should form in relatively isolated regions, with intense ultraviolet radiation fields but little ongoing star formation. They should also show chemical signatures of pristine gas, without heavy element enrichment. In late 2023, a team led by Akos Bogdan at the Center for Astrophysics, Harvard and Smithsonian, reported observations of an object called UHZ-1, detected through JWST observations of the gravitationally lensed field behind the Abell 2744 galaxy cluster. UHZ-1 appeared to be an early galaxy hosting a massive black hole. When the team obtained X-ray observations with the Chandra X-ray Observatory, they detected X-ray emission consistent with an actively accreting black hole. The most intriguing aspect of UHZ-1 was the black hole to stellar mass ratio. The black hole appeared to contain comparable mass to all the stars in its host galaxy, a situation almost never seen in the local universe. This is precisely what theoretical models of direct collapse predict, a massive black hole that formed early and quickly, before its host galaxy had assembled significant stellar mass. The timing of UHZ-1, observed at a redshift of about 10, also matched predictions for when direct collapse black holes should have been forming. However, distinguishing between direct collapse black holes and primordial black holes observationally is difficult. Both scenarios predict massive black holes appearing early in cosmic history, often with relatively small host galaxies. The key distinguishing feature might be the environment. Direct collapse black holes should be associated with intense radiation fields from nearby star formation, while truly primordial black holes would require no such association. Another alternative pathway involves not a new type of black hole formation, but rather extreme conditions that allow stellar mass black holes to grow far more rapidly than normally possible. In the standard picture, black holes grow by accreting matter at rates limited by the Eddington limit. But what if, in the dense gas-rich environment of the early universe, black holes could accrete at much higher rates? Super-Eddington accretion is theoretically possible under certain conditions. If matter is funneled onto a black hole from specific directions, if the accretion disk is geometrically thick and opaque, or if the black hole is spinning rapidly, the effective accretion rate can exceed the Eddington limit. Some theoretical models suggest black holes could grow at rates 10, 100, or even 1,000 times the Eddington limit for brief periods. If super-Eddington accretion was common in the early universe, it might allow stellar mass seed black holes to grow to supermassive sizes within the available time. The challenge is understanding what would produce the required conditions. Why would accretion in the early universe be so different from what we observe in nearby galaxies? Some models invoke the higher gas densities and different cooling properties of primordial gas, but these effects are still being explored. Yet another scenario, proposed more recently, involves the collision and merger of proto-galaxies. Peter van Dokkum at Yale University and collaborators have suggested that when two young gas-rich galaxies collide at high velocities, the collision could compress gas to such high densities that it undergoes runaway gravitational collapse, forming a massive black hole seed directly. This collision-induced collapse might produce black hole seeds of 1 million solar masses or more, providing another pathway to early supermassive black holes that doesn't require pre-existing stellar populations. JWST may have found evidence for this scenario in an object nicknamed the Infinity Galaxy, so called because its morphology resembles an infinity symbol. The Infinity Galaxy appears to be the result of a collision between two massive galaxies, complete with collisional ring structures. Between the two galactic nuclei sits what appears to be a supermassive black hole, possibly formed by the compression of gas during the collision. If confirmed, this would be the first observed example of collision-induced black hole formation. Fabio Picucci and Abraham Loeb at Harvard have proposed yet another scenario focused on the properties of dark matter. They suggest that little red dots might form in rare regions, where dark matter halos have unusually low angular momentum. Dark matter halos typically rotate, and this rotation prevents matter from falling straight to the centre. But in low-spin halos, matter can flow directly inward, creating extremely compact, dense structures. These unusual conditions might allow rapid black hole formation and growth, producing the compact luminous objects we observe as little red dots. The variety of proposed formation mechanisms reflects both the richness of the observations and our current uncertainty. Each mechanism makes slightly different predictions about the properties, environments, and evolution of early black holes. As JWST continues its observations, gathering more objects, obtaining deeper spectroscopy, and extending to longer infrared wavelengths, we should be able to test these predictions and determine which scenarios best match reality. It's also quite possible that multiple mechanisms operated simultaneously. The early universe was a diverse and dynamic place, with different conditions prevailing in different regions. Perhaps primordial black holes formed in some locations, direct collapse black holes in others, and Super Eddington accretion allowed stellar mass seeds to grow rapidly in still other environments. Understanding the relative contributions of different formation channels would itself be a major advance in our understanding of cosmic structure formation. To fully appreciate the significance of early black holes and little red dots, we need to place them in the broader context of the early universe's evolution. The period from about 100 million to 1 billion years after the Big Bang, when these objects existed, was one of the most transformative eras in cosmic history, a time astronomers call the Cosmic Dawn and the Epoch of Reionization. The story begins much earlier, in the first moments after the Big Bang. For the first 380,000 years of the universe's existence, space was filled with a hot, dense plasma of electrons, protons, and photons. This plasma was opaque to light, photons constantly scattering off the charged particles, unable to travel far before being absorbed and re-emitted. As the universe expanded and cooled, eventually the temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, suddenly rendered the universe transparent. The photons that had been trapped in the plasma were finally free to travel through space unimpeded. These photons, stretched by cosmic expansion to microwave wavelengths, are what we observe today as the cosmic microwave background radiation. But the newly transparent universe was also a dark universe. There were no stars yet, no galaxies, just hydrogen and helium gas slowly collapsing under gravity into the denser regions where dark matter had accumulated. This period, lasting from recombination until the first stars ignited roughly 100 to 200 million years after the Big Bang, is called the Cosmic Dark Ages. The universe remained dark, but it wasn't static. Gravity was at work, pulling matter into ever denser concentrations. The first structures to form were small, perhaps only 1 million times the mass of the Sun in dark matter and gas combined. Within these structures, gas cooled and accumulated at the centre, eventually reaching densities and temperatures high enough for nuclear fusion to begin. The universe's first stars ignited, ending the cosmic dark ages and beginning the cosmic dawn. These first stars, called population 3 stars by astronomers, were probably very different from stars we see today. Formed from pristine hydrogen and helium with no heavier elements, They likely grew to enormous sizes, perhaps hundreds of times the Sun's mass. They burned incredibly hot and bright, emitting copious amounts of ultraviolet radiation. And they lived fast and died young, with lifetimes of only a few million years before exploding as supernovae or collapsing directly into black holes. As the first stars and galaxies formed, their ultraviolet radiation began to affect their surroundings. Hydrogen atoms consist of a proton and an electron. When an ultraviolet photon with sufficient energy strikes a hydrogen atom, it can knock the electron free, ionizing the atom. The intense radiation from early stars and black holes created bubbles of ionized gas surrounding each source of radiation. As more stars formed and more black holes grew, these ionized bubbles expanded and eventually overlapped, gradually ionizing all the hydrogen in the universe. This process is the epoch of reionization. Understanding reionization has been a major goal of cosmology for decades. The process left imprints in the cosmic microwave background radiation, which we can measure. Observations of distant quasars, whose light passes through intergalactic gas on its way to us, allow us to probe the ionization state of the universe at different epochs. From these observations, we know reionization occurred between roughly 600 million and 1 billion years after the Big Bang, though the exact timeline has been debated. JWST's observations of little red dots and early black holes have significantly complicated this picture. Before JWST, astronomers believed they understood the sources that drove reionization. The ionizing photons were thought to come primarily from massive stars in early galaxies. Black holes might have contributed some ionizing radiation, but they were thought to be relatively rare and not particularly massive in the reionization epoch. JWST has revealed that this picture was incomplete. First, the telescope has found far more galaxies in the early universe than expected, each contributing ionizing photons. Second, and more surprisingly, it has found numerous supermassive black holes already in place and actively accreting during the reionization epoch. These black holes would have been efficient producers of ionizing radiation. But here's where things get problematic. When astronomers calculate how much ionizing radiation all these early galaxies and black holes should have produced, and how efficiently that radiation should have ionized the surrounding hydrogen, they arrive at a prediction. Reionization should have completed much earlier than observations indicate, perhaps by 550 to 650 million years after the Big Bang rather than 1 billion years. This discrepancy has been dubbed the photon budget crisis. There appear to be too many sources of ionizing photons in the early universe, producing more ionization than the data allows. Something is wrong with either our observations, our models of how galaxies and black holes produce ionizing photons, our understanding of how that radiation propagates through and ionizes the intergalactic medium, or possibly our fundamental cosmological model itself. Several solutions have been proposed. Perhaps many of the ionizing photons never escaped from their host galaxies. Stars and black holes might have been embedded in dense gas that absorbed the ultraviolet radiation before it could reach the intergalactic medium. Alternatively, maybe the process of recombination, where ionized protons and electrons recombine into neutral hydrogen, was more efficient than standard models assume. If recombination was frequent, then maintaining the ionized state of the universe would require more photons, potentially resolving the crisis. Another possibility is that our measurements of when reionization completed are incorrect. The observations are challenging, and there are uncertainties in how we interpret the data from distant quasars and the cosmic microwave background. Perhaps reionization actually ended earlier than currently believed, bringing observations into agreement with the new JWST data. But there's also a more radical possibility. Fulvio Melia at the University of Arizona has argued that the photon budget crisis, along with several other puzzles raised by JWST, might indicate problems with the lambda CDM cosmological model itself, specifically with its predictions for how time relates to cosmic expansion. He's proposed an alternative cosmological model that makes different predictions for the timeline of early structure formation and reionization. While this alternative model remains controversial and not widely accepted, the presence of multiple anomalies in JWST data has led some astronomers to question whether we fully understand cosmic expansion and the early universe's evolution. The role of black holes in reionization is particularly intriguing. If primordial black holes existed in large numbers, or if massive black hole seeds formed through direct collapse, these objects would have started emitting radiation before the first stars even formed. In this scenario, black holes rather than stars might have been the first significant sources of light in the universe, fundamentally reshaping our understanding of the cosmic dawn. Andrea Ferrara's team has explored this possibility in detail. They've shown that if primordial black holes with masses around 100,000 solar masses formed within the first few seconds after the Big Bang, they could have started accreting gas and emitting light as early as 100 million years after the Big Bang. This radiation would have heated the surrounding gas, affecting how the first stars and galaxies formed. It might have even prevented star formation in some regions while enhancing it in others. The little red dots, in this context, might represent a snapshot of a crucial transitional period. These objects appear in large numbers starting around 600 million years after the Big Bang and decline in abundance by 1.5 billion years. This timeline overlaps almost perfectly with the epoch of Reionization. Perhaps little red dots were common during Reionization because the conditions that created them, whether primordial black holes, direct collapse, or super Eddington accretion, were particularly favourable during that era. As reionization completed and the universe's overall properties changed, the conditions that allowed little red dots to form might have disappeared. The intense radiation fields needed for direct collapse would have become less common as star formation became more organised and less chaotic. The dense, gas-rich environments that might have enabled super Eddington accretion would have been dispersed by feedback from stars and black holes. Even primordial black holes, if they existed, would have accumulated significant masses by this point, perhaps transforming into more conventional active galactic nuclei, indistinguishable from black holes that grew from stellar seeds. The disappearance of little red dots after the epoch of reionization supports the idea that they represent a specific phase in cosmic evolution, a window of time when conditions allowed for rapid black hole growth through mechanisms that would later become less effective. Understanding this phase is crucial not just for explaining little red dots themselves, but for understanding how the universe transitioned from the dark, simple state following recombination to the complex structured cosmos we see around us today. The discoveries we've explored have profound implications that extend far beyond the specific objects being studied. Little red dots and early supermassive black holes are forcing astronomers to reconsider fundamental assumptions about how the universe evolved, how black holes form and grow, and possibly even whether our basic cosmological model is complete. Let's start with the most conservative implications. Even if little red dots turn out to be explainable within our current theoretical framework, they've already taught us that the early universe was far more dynamic and diverse than we previously appreciated. The rapid formation and growth of supermassive black holes, the existence of compact luminous objects unlike anything in the nearby universe, and the complex interplay between black holes and their host galaxies at early times all indicate that the first billion years of cosmic history were extraordinarily eventful. This has practical implications for how we interpret other observations of the early universe. Many of our models for galaxy formation and evolution were calibrated using observations of nearby galaxies and galaxies at intermediate cosmic times. We then extrapolated backward, assuming that the same processes operated in the early universe, just more vigorously. JWST is showing us that this extrapolation doesn't always work. The early universe wasn't just a younger version of the current universe, it was qualitatively different in important ways. For theorists, this means returning to their simulations and models with new constraints. Computer simulations of galaxy formation now need to incorporate better models of black hole formation and growth. including possibly multiple formation channels. They need to account for the apparently common occurrence of overmassive black holes in small host galaxies, something current simulations struggle to reproduce. And they need to explain why these overmassive black holes were common in the early universe, but rare today. The possibility of primordial black holes has particularly far-reaching implications. If confirmed, primordial black holes would represent a direct window into the universe's first moments, preserving information about conditions that existed when the cosmos was less than 1 second old. The physics operating at those extreme energies and densities is beyond what we can study in particle accelerators, so primordial black holes might be our only experimental probe of that regime. Moreover, primordial black holes could connect several current mysteries in physics. They might explain the early formation of supermassive black holes. They could contribute to dark matter, potentially explaining some or all of the missing mass in the universe. They might even connect to inflationary cosmology, the theory that the universe underwent a brief period of exponential expansion in its first moments. Different inflationary models make different predictions about density fluctuations, and these would affect the number and properties of primordial black holes that formed. Testing the primordial black hole hypothesis requires multiple approaches. We need more observations like those of QS01, looking for massive black holes in pristine environments with little evidence of prior star formation. We need better constraints on the cosmic microwave background, searching for the subtle imprints that primordial black holes would have left, and we need continued gravitational wave observations, looking for mergers that might involve primordial black holes with properties distinct from stellar mass black holes. Future telescopes will play crucial roles in this investigation. The Laser Interferometer Space Antenna, or LISA, a space-based gravitational wave detector planned for launch in the 2030s, will be sensitive to mergers of massive black holes in the early universe. If primordial black holes exist and merge, LISA should detect them. The Roman Space Telescope, NASA's next major space telescope scheduled to launch in the late 2020s, will conduct wide surveys that could discover many more early black holes and constrain their properties statistically. Ground-based telescopes are also crucial. The Atacama Large Millimeter Array in Chile can observe the cold gas and dust in early galaxies, revealing the environments in which black holes formed and grew. Future extremely large telescopes, with mirrors 30 to 40 meters in diameter, will be able to study individual early galaxies in exquisite detail, potentially detecting the first stars and directly observing the conditions during the cosmic dawn. But perhaps the most important tool we have is JWST itself, which is only beginning its mission. The telescope is expected to operate for at least another decade and possibly much longer. Each year brings new observations, deeper images, and more detailed spectroscopy. The census of little red dots continues to grow, with each new object adding to our understanding of this mysterious population. The telescope is also beginning to observe at longer infrared wavelengths, mid-infrared observations that can penetrate even heavier dust obscuration, and reveal black holes that might be invisible in near-infrared observations. The discoveries we've discussed have also sparked intense theoretical activity. Hundreds of papers have been published in the past 2 years attempting to explain little red dots, model primordial black hole formation, understand direct collapse scenarios, and explore the implications for reionization. This theoretical work is crucial for making testable predictions that observations can confirm or refute. One particularly active area of research involves understanding the feedback between black holes and their environments. As black holes grow by accreting matter, they release tremendous amounts of energy. This energy can heat and disperse gas, potentially preventing nearby star formation. In the early universe, where everything was more compact and connected, this black hole feedback might have played a crucial role in regulating how galaxies formed and evolved. If black holes formed first, through primordial origins or direct collapse, and then shaped their environments through feedback, this would represent a top-down model of structure formation, quite different from the traditional bottom-up scenario, where small structures form first and gradually merge into larger ones. Understanding which picture is correct, or whether both processes operated simultaneously, is a major goal of current research. Another implication concerns the nature of dark matter itself. If primordial black holes make up a significant fraction of dark matter, this would rule out many popular dark matter candidates, such as weakly interacting massive particles or axions. Conversely, the properties and abundance of primordial black holes might provide clues about dark matter's nature, even if primordial black holes aren't dark matter themselves, because their formation and evolution would have been influenced by the dark matter distribution in the early universe. The photon budget crisis and the possibility of early black hole illumination also have implications for understanding the epoch of Reionization, which in turn affects galaxy formation. Reionization heated the intergalactic medium, making it harder for small galaxies to accrete gas and form stars. The timing and exact nature of Reionization thus influenced which galaxies survived and thrived. If our understanding of Reionization is incomplete or incorrect, it could affect many conclusions we've drawn about galaxy evolution. There's also a philosophical dimension to these discoveries. For most of human history, the universe beyond our immediate surroundings was unknowable, accessible only through speculation and myth. The past century of astronomy has progressively extended our observational reach, first to nearby galaxies, then to distant galaxies billions of light years away. With JWST, we're now observing epochs that contain the universe's first billion years, pushing back to times when cosmic structures were just beginning to form. This is, in a real sense, observational cosmogony, using telescopes to study questions that were once purely philosophical. How did order emerge from chaos? What were the first objects in the universe? How did darkness give way to light? The fact that we can now address these questions empirically, with data from real observations rather than just theoretical speculation, represents a remarkable achievement of human ingenuity and technological capability. Yet with each answer comes new questions. The little red dots have revealed gaps in our understanding. Primordial black holes, if they exist, would solve some puzzles but raise others about conditions in the universe's first moments. The photon budget crisis suggests we might be missing something important about reionization, or perhaps about cosmology itself. This is the nature of scientific progress, each advance revealing new layers of complexity and new questions to investigate. As we continue to study the early universe with JWST and future telescopes, we're likely to encounter more surprises. The universe has repeatedly proven more complex and interesting than our models predicted. Perhaps we'll discover that primordial black holes are common and played a central role in structure formation. Perhaps direct collapse black holes will be confirmed as the dominant seed mechanism, or perhaps we'll find that multiple formation channels operated, with the early universe sampling all possible paths to creating massive black holes. Whatever the resolution, we're living through a remarkable period in astronomy. The questions we're asking about the universe's first billion years would have been purely speculative even a decade ago. Now they're empirical questions that observations can address. The little red dots, whatever they ultimately turn out to be, have already succeeded in challenging our assumptions and forcing us to think more carefully about how the universe evolved from its smooth, simple initial state to the rich, structured cosmos we inhabit today. The next few years promise to be exciting. As JWST continues its observations, as other telescopes contribute complementary data, and as theorists develop more sophisticated models, the picture should become clearer. We may not solve all the mysteries immediately, some will likely persist for years or decades, but the combination of extraordinary observational capabilities and intense scientific scrutiny means we're positioned to make genuine progress on some of cosmology's most fundamental questions. For now, those tiny red dots, scattered across JWST's images, remain enigmatic. But they're not just puzzles to be solved, they're messengers from the universe's youth, carrying information about an epoch we can never visit directly. In their faint light, stretched by billions of years of cosmic expansion, may lie the answer to one of the most profound questions we can ask. Were black holes, these ultimate expressions of gravity's power, present from the very beginning, born not from stars but from the primordial fire of creation itself? The search for that answer continues, one observation at a time. If you enjoyed this deep dive into the mysteries of the early universe, please consider liking this video and subscribing to the channel. Science sleep stories like this one take significant time and research to create, and your support helps make more content like this possible. Leave a comment below letting me know what cosmic mystery you'd like to explore next, and I'll see you in the next video.